Let's talk about the monomial expansion of Schur polynomials. So what have we done until now? We have, so let's say for a fixed n greater than or equal to 1, let's fix some degree as well, d greater than or equal to 1. We have shown that the space lambda n d of degree d polynomials homogeneous in n variables. This has, well, there are 4 bases now, z bases. You can look at the h lambdas, the e lambdas, well, the e lambda primes, the Schur functions. So all of this is in n variables. So this is h lambda x1 x2 xn, e lambda prime x1 x2 xn, and finally the monomial symmetric functions or symmetric polynomials. Okay, so there are these 4 classes, and each of these are parameterized by partitions of D into at most n parts. So here are 4 bases. Okay, and so on. So all of them are. And in fact, we also know something more. We actually know how to go between some of these at least. So for example, recall the following statements that we have already proved, that if you want to express h lambda in terms of, let's say, m lambda. Okay, so this is sort of something we did a long time ago, but maybe the one that's more recent. If you want to so let's say if you want to express h in terms of s. Okay, so this is what comes from most recently what we did, talking about the iteration of the Peary rule and so on. So this transition matrix is given by the formula h lambda is the sum k mu lambda s mu. Okay, where again mu ranges over p dn. Now similarly, we also know how to do e lambda prime in terms of s lambda. Now let me sort of remind you of something that we did quite a while back, which is writing h lambda in terms of the m's, the monomial symmetric function. That formula look like this: h lambda is the sum m lambda mu m mu. Okay, again mu over p dn, and these numbers m lambda mu, if you go back and look at that lecture, are the following. This is the count of the number of matrices with non-negative entries. So let me call it Z plus matrices. Okay, of size length of lambda cross length of row, but actually I can just assume the size is n cross n if you wish. Okay, because I've assumed throughout that lambda and mu, all the lambdas and mu's here are have at most n non-zero parts. So I can enlarge my matrix size. I take size n cross n such that the row sums, the matrices, their row sums are lambda and their column sums are given by the vector mu. Okay. So first row sum is lambda 1, second row sum is lambda 2, first column sum is mu 1, second column sum is mu 2, etc. Okay, so this is this was the number m lambda mu. Okay, now the thing that we haven't really talked about, so and likewise we have a similar thing for the e's. Okay, so everything that we know about the h's, there is sort of a dual statement for the e's as well. But what I want to talk about today is sort of this missing link. How does one write s in terms of m? Okay, now the thing is, of course, implicitly it is known, because whenever you have, say, 3 bases of the same space and you know how to change the first one to the third one as well as the first one to the second one, then you can go between the second and third bases sort of by inverting the relation. Okay, so let's write that out explicitly. What I mean is this, so let's call that transition matrix something. Okay, let's define, when you write s lambda in terms of the monomials m mu, let's call these guys something. So I don't know, x, capital X lambda mu maybe. Okay, so suppose that's what it is, then here's the here's how you would relate the three. So then you know the relationship between h lambda of x. So let me just suppress the variable x here. So h lambda is the sum over mu of k mu lambda s mu, and so this is now sum k mu lambda. And how do you write s mu in terms of other monomial symmetric functions? I have to use my capital X here. So capital X mu, and let me change this lambda to a gamma, m gamma. Okay, so this is h lambda of x is s mu of x, m gamma of x. Okay, so that's going to tell me how to write h lambda in terms of m gamma by multiplying out the two relations. But on the other hand, I already know how to do this. This is given by that matrix capital M lambda gamma times m gamma of x. Okay, now the sum runs over. So sorry, this sum actually runs over both mu and gamma. Okay, now comparing these two, so what do I get when I compare these two equations? So I know these two are the same. It sort of tells me how to get my capital X from my m's and k's. Okay, so if you recall, so if let's just form these matrices. So let's call this matrix script k, which is the matrix whose entries are, the mu lambda entry is k lambda mu. Okay, so this is the lambda comma muth entry of this matrix. And recall, we had sort of made this more precise. You arrange the partitions in PDN sequentially as lambda 1, lambda 2 and so on, such that which is compatible with respect to the dominance order. Okay, so that's one way of doing it. So script k is just the matrix of Koska numbers, the Koska matrix. Script x maybe or chi is the matrix whose entries are the transition matrix between the Schurs and the monomials, and script m is the matrix whose entries are m lambda mu. Okay, so all these matrices run over all pairs lambda mu in PDN cross PDN. Okay, good. So what does that mean? The matrix relation is therefore the following. So if you go back and see what this equation says, it says summation k mu lambda x mu gamma over all gammas should give me m lambda gamma. Okay, so this is just the equation that the script m matrix is nothing but the k transpose matrix times the x matrix. Okay, there's a transpose there because this is mu lambda rather than lambda mu. Okay, so this is the relation between the three matrices, and this is what I meant by saying that since you know two of them, you know m and the script k matrix, this determines the coefficients x lambda mu by means of this inverse. This is nothing but k transpose inverse times m, and it is whatever it is. Okay, so you get some numbers, but here's the interesting statement that we want to make, and this is surprising in some sense. So it says the following: these coefficients x lambda mu that we just defined are actually nothing but the Koska numbers themselves. So this is for all lambda mu in PDN. Okay, in other words, this matrix kappa transpose or k transpose inverse m is actually just the matrix script k itself. Okay, in other words, this matrix k transpose inverse m is just the matrix k itself. Okay, now what does this final equation mean? So let's just see what this would involve. So observe this equation here says m is therefore k transpose k. Okay, in other words, the lambda muth entry of m, if you want to compute it, it's actually the following: it's you take kappa transpose, so I have to sum, so maybe I will use gamma here like I did in the earlier case. M lambda gamma is the sum over all mu's of k, so k transpose, so it's mu lambda and k mu gamma. Okay, so this is basically what we are claiming. The content of this theorem is really the following equation or the identity which holds between the M matrix and the K matrix. Okay, that the M matrix is just K transpose K. In other words, M lambda gamma is this sum. Okay, now let's just see what what the proof therefore should involve. So how would one prove this? Well, to prove this, we will sort of just think about this combinatorially. Okay, so remember, both sides of this equation count certain combinatorial objects, or each of them is the cardinality of a certain combinatorially defined set. Right? What is M lambda gamma? As we just saw, this is the cardinality of the set of integer matrices. Let's even say n cross n. We have fixed an n cross n integer matrices whose row sums are lambda and column sums are gamma. Okay, and what's on the other side? So in some sense I don't need to fix an n. So we've said this before. If your n, as long as your n is bigger than lambda, the lengths of lambda and gamma, it doesn't really matter. So in this case, now let me say, okay, anyway I'm going to get the same cardinality. Let me just say I will take integer matrices whose sizes are length gamma cross length lambda. Okay, so instead of this I could even say this, it's matrices of size length gamma cross length gamma, length lambda cross length gamma matrices. Okay, with row sums lambda and column sums gamma. Okay, so this is the cardinality. This is a set whose cardinality is M lambda gamma. And now let's look at the right hand side. What is it the cardinality of? Well, K, the Koska numbers are actually cardinalities of certain sets, subsets of semi-standard Young tableau, right? So if you sort of see what this really counts, well, K mu lambda is the set of semi-standard Young tableau of shape mu and type lambda. Okay, so this is, well, the right hand side is actually pairs of semi-standard tableau. So this is the cardinality of the following set. Take pairs PQ, where what are P and Q? P and Q are both semi-standard tableau. They both have shape mu. Okay, so P is a semi-standard Young tableau of shape mu and type lambda. Okay, and Q is a semi-standard Young tableau of shape mu again and type gamma. Okay, and the cardinality of this set of pairs satisfying these conditions is exactly this particular term K mu lambda K mu gamma. But then I also want to take a union over all possible mu's, right? Because I want a summation over mu here. Okay, mu ranging over PDN for all partitions. Now what is that? I can rewrite this union therefore as follows. I don't care what mu is. That's what this union means, right? So I will just say, well, that just means this right hand side is the following set. It's all tuples of semi-standard tableau of the same shape. Okay, PQ are both semi-standard tableau, Young tableau, with the following properties, that they both have the same shape. I don't care what that shape is. Shape of P equals shape of Q. Okay, but the types are fixed. Type of P is lambda and type of Q is gamma. So this is the set that I'm looking for. Okay, and what this identity says is that the set of integer matrices with row sums lambda and gamma is that set has the same cardinality as the set of pairs of young tableaux which satisfy these conditions. Okay, and of course, as you've seen many times already in this course, one of the ways of thinking about proving identities like this is to see if there is a bijection that one can construct somehow algorithmically or using other input data. Now, it turns out that there is in fact a very nice bijection between these two sets, and a very famous bijection. So this is called the Robinson-Shenstead bijection. So let me just state this as a fact for now, or just tell you what the Robinson-Shenstead the RSK bijection is a bijection between these two sets. Okay, so the RSK bijection is a bijection between exactly these two sets. Okay, which two? This one, this set of pairs, and on the other side, on the left hand side, the set of integer matrices with given row and column sums. Okay, so it establishes a bijection between these two sets, and so we will defer the proof of this to a different lecture. So the RSK, it's a very beautiful algorithmic bijection which tells you, given a matrix of that kind with row and column sums being prescribed, how does one construct tableau? Okay, and this is called Shenstead insertion, the insertion algorithm and the bumping algorithm. Okay, so we will defer this to a different lecture. Okay, but if you assume that there is in fact such a bijection, then we are done, right? Because then the m lambda mu is the same as the product of the matrices script k transpose times k, and that establishes the original theorem that I said, which is that when you go from the basis s to the basis m, the transition coefficients are exactly the k lambda mu's. Okay, the Koska numbers. Okay, good. Now let me just point out an interesting corollary of this statement, which is the following. So if you write, okay, let me write the statement out first. So let lambda be a partition of D into at most n parts, then the Schur function S lambda of n variables x1, x2, xn has the following prescription. So you do the following: you look at all semi-standard Young tableau of shape lambda. Okay, and of course each of them will have various types. So look at all semi-standard tableau of shape lambda, and which are fillings with the numbers 1, 2, 3 till n. Okay, so I fixed an n. So now what I'm going to do is I look at the shape of lambda and I fill it with the numbers from 1 to n. Okay, I allow those numbers. Not all numbers need to appear. And for each such filling, I do the following. I look at x raised to the type of that filling. Okay, the type of that tableau. So remember, the type of a tableau is actually an n tuple. Okay, it's a multi-index which keeps track of how many ones there are, how many twos there are, how many threes there are, and so on. Okay, so the claim is that here's how the Schur function can be obtained. You just run over all semi-standard Young tableau of given shape with the fillings being numbers from 1 to n, and then for each such tableau you look at a certain monomial, which is x1 raised to the number of ones which appear, right? That's the type of T. x2 raised to the number of twos that appear in the filling, and so on. Okay, let's just quickly look at an example. So suppose I take n equals 3, and if I take lambda to be the shape 2, 1. Okay, now let's see what the corresponding Schur function has to be in 3 variables, 1, 2 and 3. So I have to try and construct all semi-standard Young tableau of shape lambda in which the numbers can be 1s, 2s and 3s. Okay, now what all can I do? Well, here are the various possibilities. So I can put 1s in both and 2 in this. 1s in the first row, 3 here. Okay, so that's done with the 1s. 1, 3, 2. Okay, now I try putting 2s. Okay, so I've already missed another one here. So let's look at 1, 3. Okay, so that seems to be it. So I guess I've gotten all of them. So there are 8 semi-standard tableau with shape being the partition to 1, and in which I am allowed to use the numbers 1, 2 and 3. Okay. Now what does the corollary tell us? It says to each such tableau, each such filling, you just form a monomial which is x raised to the type of that filling. Okay. So what does that mean? So let's do it in turn for each of them. What monomial will we associate to this last one, for example, 1, 2, 2. So in this tableau, 1 appears. So what's the type of this guy? So if we take this fellow, what's the type of this matrix? The type is of this tableau, it's how many times 1 appears, how many times 2 appears, and how many times 3 appears. So 1 comes once, 2 appears twice, 3 doesn't appear at all. So the type of this filling is 1, 2, 0. Okay, let's look at another one. This guy, the type 1 occurs once, 2 occurs once, 3 occurs once. Okay, and so on. So for each you associate a type, and when you have a type, you can look at the corresponding monomial x raised to that multi-index 1, 2, 0. Okay, which according to our notation just means x1 raised to 1, x2 raised to 2, x3 raised to 0. Okay, so this is the monomial which you associate to this tableau here. Okay, so that's just x1, x2 squared. Okay, so it's easy. You just, wherever you see a 1, you think of it as x1. Wherever you see a 2, you think of it as x2, and so on. So there's just a single 1 and 2 2's here. So this particular tableau counts for x1, x2 squared. Okay, and so on. So these two tableau here, they both give you the monomial x1, x2, x3. x1, x2, x3. Okay, and so on. So if you try and write out what each of them looks like, this one is x1 squared, x2. This is x1 squared, x3, x1, x3 squared. This is x2 squared, x3, x2, x3 squared. Okay, now so I've written out what the monomials are for each of these 8 guys, and if you sort of see what you got, finally it's the following. It's xi square xj. Okay, all things of that form, I not equal to j. Okay, so I should allow them to be numbers from 1 to 3, I not equal to j. So there are 6 possibilities like this. Okay, and let's see what else can I do. And then there are 2 more terms which are 2 times x1, x2, x3. Okay, and if you wanted to rewrite this in terms of monomials, this is nothing but the monomial symmetric function corresponding to, so what is this? This is 2 and a 1, right? So this is 2, 1, 0, the monomial symmetric function corresponding to the 3 tuple 2, 1, 0 if you wish, plus 2 times the monomial symmetric function corresponding to 1, 1, 1. Okay, in 3 variables. So each of these is these are evaluated in the 3 variables x1, x2, x3. Okay, so that's what the corollary tells us. Okay, now let's just see how one obtains the corollary from the original theorem. Okay, so this is a beautiful corollary, because in some sense it says that you can think of the Schur functions as really being some sort of something which counts or keeps track of weights of semi-standard Young tableau of shape lambda. Okay, so Schur functions on the one hand, semi-standard Young tableau of shape lambda on the other. You should think of the Schurs as being some function which sort of gives a weighted sum or keeps track of the weights of this set of semi-standard Young tableau. Okay, now let's see how one would obtain this from the theorem. So as I said, I'm not going to prove the theorem because well, if I assume the RSK bijection, then the theorem is proved. So we'll come back to the RSK later, but for now my interest is in showing you how the theorem implies the corollary. Okay, so what was the theorem? It said that the Schur function S lambda is the monomial expansion. Okay, now the corollary says that the Schur function has another expansion. Okay, what was the corollary? It says Schur function x1 x2 xn is actually just the sum x raised to the type of t running over all semi-standard Young tableau shape lambda. Okay, and fillings from 1 to n. Okay, now let's see how you would get one from the other. It's almost there. You can sort of see the semi-standard tableau. Now k lambda mu, recall, is the number of semi-standard tableau. So let's start with the theorem. We know this. So this is sum over mu, and k lambda mu, recall, what is this? This is just the number of semi-standard Young tableau shape lambda and content mu. And what's m mu? Well, m mu itself is a sum, right? It's going to have, well, it will have the term x to the mu, but it will also have all other terms of the form, say, x to the alpha, other monomials, where what is alpha? Alpha is a multi-index such that when you it's a permutation of mu. Think of alpha as a permutation of mu. When you sort it into descending order, you just get mu. Okay. So let's just say alpha sorted in descending order. So recall this is one of the notations for that, is going to give you the partition mu. Okay, so you already see something here, which is that the coefficient of x power mu is matching correctly with what the corollary predicts, right? Because when you run over all semi-standard tableau of shape lambda and those with, say, type mu, so content is, sorry, another word for type. So when you run over all tableau of shape lambda and type mu, the corresponding contribution is just going to be x power mu, right? And how many times will that term x power mu occur? It will occur as many times as there are semi-standard tableau of shape lambda and type mu. Okay, so definitely if you look at the corollary, the coefficient of x power mu here is exactly what the theorem predicts. But this goes a bit further. It says that even the coefficients of the other monomials, x power alphas, are given exactly by this very same number. Okay, so what this finally amounts to is the following. Let's phrase this as a lemma. So to prove the corollary, it's enough if we show the following lemma, okay, which is the following: let alpha be any multi-index such that when you sort it, alpha is a permutation of mu. Okay, when you sort it in descending order, you get mu. So I fixed mu. Fix. Okay, then. So let me also fix a lambda. Then the Koska number k lambda mu is actually the same as the Koska number k lambda alpha. Okay, and observe, just think for a moment, you'll see that once the lemma is established, then the corollary is established. Okay, because the theorem says that the coefficients that you will get in front of x power alpha is also k lambda mu. Okay, but the corollary says that in front of alpha, the coefficient of x power alpha should actually be k lambda alpha, the number of semi-standard tableau of shape lambda and type alpha. Okay, so the claim is that whether you take alpha or mu, the number of semi-standard tableau is the same. Okay, and the proof is actually very simple. So recall, how did we get these k lambda mu's? They actually originally arose when you attempted to take products of h mu, right? How did you get? So what was h mu? This is h mu1, h mu2, h mu whatever. So let me assume mu has been, I pad it with some extra zeros so that it finally has n parts. Okay, so I keep doing this. So some of them might just be zeros, h zeros. Now what is h sub alpha, if you wish? That's just, well, I mean, by which I mean, let's just define it like this. It's the product h alpha 1, h alpha 2, h alpha n. Okay, it's just the product of those numbers. But observe that alpha and mu are actually those two tuples are the same up to some permutation. Right? I take mu and I permute those numbers around, I get alpha. But therefore these two are the same, because this is just the product of the individual parts of mu or the individual parts of alpha. So they both give you the same answer. So what does this mean? This says that, well, if I go back and see how I got my k lambda, well, how did I get my k mu lambdas? Observe, if you attempted to write h mu as a sum of my Schur functions. So here my mu's and alpha. So let me change this to lambda. Then this is this is k lambda mu. Okay, this is some more lambda. So this was my this is sort of how I got the k. So if you go back and see how the k's actually arose, you did the Peary rule again and again, and what you finally got were these towers and so on, which we identified with semi-standard Young tableau of shape lambda and type mu. But you just go back and do that proof again with h alpha instead of h mu, meaning you multiply the h's in some other order. Okay, not necessarily mu1, mu2, mu-n, which are in descending order. You can permute it any way you want. Okay, but that iterated Peary rule proof works just the same, and what you get again is a tower. Okay, so you have to keep attaching boxes and so on. And what you need? Well, the coefficients that you get are of the following kind, that the final shape is lambda, but you have alpha 1 ones. Okay, the very first step you've got a shape. So let me just quickly remind you of what happens. So I have alpha 1 ones, then I have to attach some 2's. So that's alpha, whatever, this plus this is alpha 2. Then I attach some 3's, alpha 3 3's, and so on. So that process actually works the same way. So you should go back and take a look at the proof again. It's very instructive. It didn't need that the alphas are in descending order or the mu's are in descending order. It works just the same. Okay, so therefore, since these two are equal, it of course forces, since the S lambdas form a basis, the expansions are unique. So this actually tells you that the Koska number k lambda mu must be the same as the Koska number k lambda alpha. Okay, so that concludes the proof of the lemma and thereby the proof of the corollary. Okay, so as I said, we are sort of still, the Robinson-Shenstead is still left over.